Okay, so we are moving on to chapter 20, which is all about hypothesis testing. So there's a lot to cover regarding hypothesis testing. So the book breaks it up into a few chapters. So we'll do chapter 20 and then do chapter 21 and so on and so forth. And it's just continuing this idea of inference where we want to understand something about the population, but we can only observe limited data. So we observe a sample, and based on this limited data that we see in the sample, we're going to make a conclusion about the population. So here, we're still dealing with categorical variables, okay? So, hypothesis testing for categorical variables, and we're just going to start off with what we call a one proportion z-test. One proportion because we're just dealing with one categorical variable, one proportion, one sample. And it's a z-test because it's based on the normal distribution. And the idea is this, okay? You know, we observe a sample, okay, and the sample has some proportion p hat. Okay, so maybe the proportion in our sample is 23%. Okay. Meanwhile, we have an idea of what the population looks like, okay? Have an, quote, idea or hypothesis about the population. So here's a population, and we think that the population has some proportion p0, okay? So maybe someone says the population is 30% this, okay? And we take a sample and it's only 23% that. So the question is, because I saw a sample where the proportion is only 23%, does that refute this claim or idea about the population? Okay. So if my sample has proportion p hat, which is different from the proportion p0, which is a belief about the population, does this data refute our belief about the population? Okay. That's the basic premise behind hypothesis testing. Okay? So we say, we think the population has some proportion p0, but we can't observe the population directly, so we take a sample. The sample has some proportion p hat. Okay? P hat is not exactly the same as p0, so does that contradict our statement? Or is it possible that this is actually true and that my sample is just a result of random chance? Okay? So here's a simple example. someone says they have a fair coin. Fair coin means we're expecting it to land heads 50% of the time. Okay? But let's say we flip the coin 1,000 times and it lands heads 800 times. Okay, so our proportion is p hat is 800 versus we're expecting 500, 50% heads. Does the fact that the coin, whatever we did to it, land 80% heads, cause us to believe that the coin does not flip fair? And you would say, probably, yes, okay? So if someone is flipping a coin and they're managing to get 800 heads out of 1,000 coin flips, you would either have to come to the conclusion that they're cheating when they're flipping the coin, or the coin isn't fair, or something, okay? On the other hand, if somebody says, I've got a fair coin, and they flip the coin 10 times and it lands heads 8 times, 8 times out of 10, would that cause you to believe that the coin is not fair? No, because that seems like, even though it's still 80% heads, getting 8 heads out of 10 doesn't seem that strange of an outcome, okay? It doesn't happen all the time, but it happens often enough in our lives that, that we could say, you know what, the coin might still be fair, and we might have just seen an unusual thing. Is that okay? So, our conclusion to this question, okay, if my sample has proportion p hat, does that refute p0? This conclusion is based on what we call a p-value, okay? So we calculate a p-value. Okay, and what is a p-value? A p-value is a probability, okay? Is the probability of observing our data. Or something more extreme. If we assume that I'm going to write this term here, the null hypothesis is true. Okay, the null hypothesis is basically the belief that the population has proportion p0. Okay. So when our p-value is large, then that means if the null hypothesis is true, there's a decent probability or a large probability of observing our data. On the other hand, the p-value could end up being small, and that means if the null hypothesis were true, it is unlikely for us to observe our data. So a large p-value would not refute our belief about the population, would not refute the null hypothesis. Meanwhile, a small p-value would cause us to question or reject the null hypothesis. Okay. A large p-value would tell us not to reject the null hypothesis. Okay. It is probable, or it is not unlikely, for us to observe our data or I'm going to just write or something more extreme, SME. Okay, so this is a common phrase that I'll put up. Something more extreme if the null hypothesis and the null hypothesis is abbreviated H0 is true. And on the other hand, a small p-value tells us it is unlikely for us to observe our data or something more extreme if the null hypothesis is true. Okay, so this causes us to reject the null hypothesis. We will talk about when the p-value is large versus small, okay? But for now, our rule of thumb, okay? Rule of thumb is that if the p-value is bigger than 0.05, that means the p-value is large. Do not reject the null hypothesis. And on the other hand, if the p-value is less than 0.05, the p-value is small, reject the null hypothesis. Okay. We'll talk about when we should use something other than 0.05. Okay, but that will come in a future lecture.
What if it's exactly 0.05?
Then I guess it's up to you. That rarely happens. That rarely happens. Okay. All right. So let's try an example here. Okay. Okay, so let's say I don't know. Are male births more common than female births? This is what we want to know. Okay? So we're going to test this, okay? And so we if we're asking, are male births more common than female births, what's the underlying inherent, I guess, assumption about the population? The underlying assumption would be that the proportion of male births and female births are equal, or the proportion of male births should be 0.5, and we want to know, do we have data that supports, is the proportion actually greater than 0.5? Okay, so our null hypothesis is along the lines that male and female births equally common. So I would write my null hypothesis, so H0 is that P, the proportion in the population, is equal to 0.5, okay? So this 0.5 right here, this is our P0, okay? So this states that the proportion of male births is equal to 0.5. And then the alternative hypothesis would be that P is greater than 0.5, okay? This states that male births are more common. Also, so you're going to use the same number in both the null hypothesis and the alternative hypothesis, and those are, that number that you use is P0. Okay? So your null hypothesis says P is equal to P0. The alternative is that P is greater than, P is less than, or P is not equal to. In our example, it is that P is greater than 0.5. So then we have to gather data to see if we have any evidence to support or reject our null hypothesis. Okay, so let's say we gather a bunch of birth records from a bunch of hospitals. Okay, random selection of birth records. So let's say we get 900 birth records, and the number of males is 470. Okay, so my p hat is what? 470 over 900. I'm getting 0.522. Okay. So again, we're looking for our p-value, which is the probability of observing our data, or something more extreme, if the null hypothesis is true. So if the null hypothesis is true, then p is equal to 0.5. All right? And so we can create a sampling distribution for p hat. Okay? So we make a sampling distribution of p hat. Okay? And what would the properties of the sampling distribution have?
Normal distribution.
Normal distribution. And what would be the mean?
0.5.
The mean would be 0.5. And the standard deviation would be square root of 0.5 times 0.5 divided by 900. Okay? Because if the null hypothesis were true, this is what our sampling distribution for p hat would look like. So here I am at 0.5, and our standard deviation, let me just do this, 0.5 times 0.5 divided by 900, so I get 0.01667, okay? But what did we observe? We didn't observe a proportion of 0.5, we observed a proportion of 0.52222, okay? And so we want to know, if the null hypothesis were true, what's the probability of us observing a random sample where the proportion is 0.522? Okay. So this is, we get a z-score, and I'm going to do 0.5222. So this part should be very familiar to you guys. Divided by, minus 0.5 divided by 0.01667. So I get a z-score of 1.33. Reference to this guy. Okay, so how much is in the area to the left of 1.33? 0.09, or to the right of 1.33? 0.0918. Okay. So our probability, 0.0918. So this says that if male and female births are equally common, okay, or basically that the null hypothesis is true, okay. So if the null hypothesis is true, or if male and female births are equally common, the probability of us taking a sample of 900 births and observing 52% male births, okay? So we're not observing 50% births, male births, we're observing 52% male births. The probability of that happening based on random chance, okay? Meaning just from the random selection of 900 birth records. Because if I go into the population and select another 900 birth records, I'm going to get a different number here, okay? So how likely is it for me to get 52% male births just from a result of the random selection procedure? That happens about 9% of the time, okay? So if male and female births are equally common, the probability of us seeing 52.2% male births or more, or something higher, based on random chance alone, is 0.0918. Okay. My rule of thumb that I've given you right now is that if that probability is over 5%, then we're not ready to disregard the possibility that it happened by random chance, okay? We can't ignore, there's about a 9% chance of us observing a sample like this, or something bigger, even when the null hypothesis is true. So we're not ready to ignore it, so we are not ready to say that we have data to refute the null hypothesis, okay? So So our p-value is large. Okay. So we are not ready to refute or reject the null hypothesis. Yes?
Do you have a lab today?
You do have a lab section today. I think I'll have the TA go over more of this hypothesis testing stuff, just because it's new and unfamiliar. So
Which value is
probably not.
Which is the zero value?